Hi, and welcome to this review of logarithmic functions. Like all mathematical functions, logarithms are used to measure and model real-life occurrences. From sound measured in decibels to the magnitude of earthquakes measured on the Richter scale, logarithms are used to relate these natural occurrences to a baseline measurement. In addition, logarithmic functions have an inverse relationship with exponential functions, meaning that they undo each other. This allows us to use logarithms as a tool to solve exponential equations. If you want to try some of the examples in this video on your own, grab a scientific calculator and be prepared to practice some skills and explore the power and properties of logarithmic functions. Let's get started. Before we start our work with logarithms, let's take some time to review the basics of exponential equations. The components of an exponential equation are shown here in blue. A base of 2 raised to the power of 3 is equal to 8. The answer, 8, is referred to as the argument. Rearranging these components allows us to write the inverse logarithm as shown highlighted in green. This illustrates nicely that logs are the power of a named base. Let's practice identifying these components and rewriting a few exponential equations as logarithmic equations. Normally we would say 5 squared equals 25. If we were to use the terms we used in our first example, we could say a base of 5 raised to the power of 2 is equal to 25. Now let's rewrite this as a logarithm. Log base 5 of 25 equals 2. Let's try another one. If you'd like to try this out on your own, pause the video and give it a shot. We would say this as a base of 4 raised to the power of 3 is equal to 64. If we rewrite this as a logarithm, we get this. Log base 4 of 64 equals 3. When we evaluate a logarithmic expression, we ask ourselves, what do I have to raise this base by to get the value of the argument? Logarithms are the power that is needed. Now, let's focus on the notation of logarithms. In our first example, the base of the log was 5, and our second example had a base of 4. Note that the base is indicated as a subscript on the word log. This will be true for logs with bases other than 10 and their irrational number e. Logarithms with a base of 10 do not indicate the base in the notation, and they are called common logs. There is a key on the scientific calculator for common logs. If you have a calculator in hand, try inputting the following. Log of 1,000. The answer is 3. Which means that 3 is the exponent needed to raise a base of 10 to get 1,000. See if you can guess the answer to this one before you see the answer. Log of 10. Think you've got it? The answer is 1. A base of 10 raised to the power of 1 will result in 10. There is also a key for the natural log function, which reads ln. Whenever you see this notation, you know that you are dealing with a base of e. Exponential functions that deal with continuously compounded interest or population growth models have a base of e. The natural log is used to solve such applications, but that's a topic for another time. As mentioned earlier, the Richter scale measures the amplitude of waves that result from seismic activity and uses a logarithmic formula, r equals log of a over b, where a is the observed amplitude and b is a baseline measure. If the amplitude of a wavelength is measured at 450 times the baseline, the formula would read as r equals log of 450 times b over b, which simplifies to r equals log of 450. Entering this in your calculator results in a value of 2.7 rounded to the nearest tenth. This measurement reflects the exponent on a base 10 and would be considered a fairly minor earthquake on the Richter scale. Like all inverse functions, the graphs of exponential and logarithmic functions are symmetric about the identity line y equals x. Graphing a logarithmic function is as simple as creating a table and plugging in values until the curve takes shape. Some students find it easier to convert the logarithm to an exponential function and flip the domain and range values to get the mirror image graph. Let's give that method a try. Graph the exponential function f of x equals 3 to the x and the logarithmic function g of x equals log base 3 of x on the same graph. There are several properties of logarithms that allow you to rewrite expressions in order to simplify them. I will list the corresponding exponent rule that you are already familiar with that supports the logarithmic function. Given what we have already covered with respect to exponential expressions, the first three should seem rather intuitive. Property number 1, log base b of 1 equals 0. Remember to ask yourself, what base of b raised to the 0 power will give me an answer of 1? Well, we know that any base raised to a power of 0 equals 1. b to the 0 equals 1. Property number 2, log base b of b is equal to 1. This also makes sense because raising any base to a power of 1 is equal to the base. b to the 1 is equal to b. Property number 3, log base b of b to the n is equal to n. This is similar to property number 2, but the exponent n can be any value. b to the n equals b to the n. Thinking about the inverse relationship with an exponential also may be helpful here. Taking the log of an exponential undoes the exponential. The result is the input n. The next three properties are more arithmetic and are used to simplify or expand logarithmic expressions. I will provide some examples for each of these properties. Property number 4, the product property. This is read as log base b of m times n equals log base b of m plus log base b of n. The key with this property is that you can expand the log of a product to the sum of logs with the same base. This relates to the exponent rule, a to the m times a to the n equals a to the m plus n. Here's an example. Write the logarithm as a sum and simplify if possible. For this, we'll use property number 2 to simplify the first term of the expression on the right. Log base 4 of 4 is equal to 1. So this gives us 1 plus log base 4 of 6. Here's another example. Write the logarithm as a sum and simplify if possible. Log base 3 of 9 times x is equal to log base 3 of 9 plus log base 3 of x. To simplify it, let's rewrite 9 as 3 squared. So we have log base 3 of 3 squared plus log base 3 of x. Then we'll use property number 3 to simplify further. This gives us 2 plus log base 3 of x. Let's take a look at another property. Property number 5, the quotient property. Log base b of m over n is equal to log base b of m minus log base b of n. As you can see, the log of a quotient can be expanded into the subtraction of two logs of the same base. The associated exponent rule is a to the m over a to the n is equal to a to the m minus n. Let's practice expanding a logarithm using this property. We need to be sure to keep the bases the same for the subtracted terms. The first term of the expression on the right can be simplified by writing 49 as 7 squared. So here we have the log base 7 of 7 squared minus log base 7 of 3x. Now we can simplify with property number 3. This gives us 2 minus log base 7 of 3x. Now let's work on the property backwards to condense the subtraction of logs with the same base to a quotient. Now we're going to create the quotient. Log base 5 of 9 over 3. Simplify the quotient. Log base 5 of 3. You have condensed the expression to one log. The next property involves the exponent on the argument of a logarithm. Property number 6, the power property. Log base a of x to the p is equal to p times log base a of x. Note that when the argument is raised to a power, the expression is equal to the exponent being multiplied by the logarithm. The associated exponent rule is a to the m to the n power is equal to a to the m times n. We will practice implementing this property with a more comprehensive example, just to keep things interesting. Notice that there's no subscript indicated. What is the base? Remember, if there's no subscript indicated, the base is always 10. Now we need to identify the power property in the second term. The multiplier of the 3 before the log translates to the argument of 3 being raised to the third power. So this is the same as saying log of 2 plus the log of 3 to the third power minus the log of 9. Use the product rule to combine the sum of log of 2 and log of 3 cubed. This gives us the log of 2 times 3 cubed minus the log of 9. Now use the quotient rule to condense the subtraction of common logs to a single common log. This gives us the log of 2 times 3 cubed over 9. Simplify the quotient by canceling out the common factor of 9. For a final answer of log of 2 times 3, which is equal to a log of 6. For our final practice problem, let's go the other way and expand a single log into an expression of addition and subtraction. First, we'll expand the quotient into subtraction of 2 logs, base 3. Then, we'll expand the product in the first term to the sum of logs, base 3. Now we need to identify the power property in the second term. Move the exponent of 2 to the front of the log as a multiplier. Simplify the first term using property number 2. Okay, that about wraps things up. I hope that the examples we worked through have helped you better understand logarithms, their relationship with exponential functions, and the properties that allow us to simplify complex expressions. Thanks for watching and happy studying.